Almost one. So question 1, you are given a description of a DFA, and the question is construct a DFA. So number 1 is W such that W does not contain the substring zero, zero, one. Okay, so give me the idea. What's the idea behind does not contain? How do we construct a DFA for the language that does not contain a certain substring?
That means it's always accepted as long as it doesn't go in the order of 0, 0, 1. So all states other than the last one would be accept states.
Okay, so how does it relate to the DFA for the language that does have this substring? What's the relation? So let's draw so this is for accepting the substring 001. Of course, we'll have a 001 appearing somewhere. And in fact, the DFA for 001 is going to be this. So let's first draw the DFA for the DFA that contains this. So it's going to have this as an accept state. Then after you recognize this, you can have anything. And then, what? So let's do contains first. So forget about the does not for now, temporary. So 001, so if I get a 1 here, where do I go?
Stay there.
You stay. If I get a 0, if I get a 1 here,
Then
You return to start.
you go back, because I'm still looking for a 0, 0. Okay, if I get a 1 here,
You go full.
substate.
so if I get a 0, the expected is 1. If I get a 0 here,
It loops on itself.
yeah, loops on itself. So this is the DFA for the W contains the substate. Now, how do I make it does not contain?
Just
The first stage is
invert
the final.
accept.
Yeah, exactly. So the accept state becomes a non-accept, and the non-accept states become accept states. And this is a general rule, by the way. So I just make this a non-accept state, and I make the non-accept states accept states. Okay? So I swap accept with non-accept. Every accept state becomes a non-accept, and every accept becomes a non-accept, and every non-accept becomes an accept state. And this is a general rule that you can always do for the complement of a language. So if you are given a DFA for L, you can construct an NFA for the complement of L using this by swapping accept and non-accept states. Now, the idea here, something to keep in mind, is that this doesn't apply to NFAs. It applies to DFAs, but it does not apply to NFAs. So if I give you an NFA for the language, say, ends with 1, okay, so this is an NFA for the language W such that W ends with 1, right? Now, if I try to do the same thing, will I get an NFA for the language W such that W does not end with 1? If I do this, what will I get? This accepts anything. So I will get sigma star. I will not get the complement. So by swapping accept and non-accept in an NFA, you will not get an NFA for the complement. But if you swap accept and non-accept states in a DFA, you will get a DFA for the complement. And the reason behind that is that in the DFA, everything is explicit. Everything is shown explicitly. But in the NFA, because the rejection in particular is shown implicitly, and because you have multiple options, this is not going to work on the NFA. So keep that in mind. Oh, so we learned something about the DFA for the complement. So let's switch to the next language. W such that W has an even number of ones and an odd number of zeros. Even number of ones and an odd number of zeros. Okay, now give me the idea behind this. Give me just the idea or the approach. How many people solved this correct? Okay, yeah, so what's your approach?
First, I draw the DFA for even ones, and then do another one for zeros, and then a union together.
And then you do what?
A union between them.
Well, the rule for the union that we have studied applies to NFAs, not DFAs. So we union using an epsilon transition, right? And that's an NFA thing. It's not something that we can do with DFAs. So how many states did you use?
4.
Okay, 4 states. And what are the 4 states?
So
what does each one of them mean?
Q1 or Q0, whatever you want to remember. So that's a non-accept, and that's where you start. And it'll shoot out Q2 if you get a odd number of ones.
Okay, so it's true that we need 4 states, but there is a clear description of what each of these 4 states means. What do you think each one of these 4 states should mean in this case? We're tracking the number of ones and the number of zeros, and for each one of them, it can be either odd or even. So for the number of ones, it's either odd or even. For the number of zeros, it's either odd or even.
Yeah.
So at any point, we have a combination of odd, odd, even, even odd, or even even. This is the key idea. So you have exactly 4 combinations. So you start with even, then you have even, odd, even, and odd. And this is the idea.
Yeah.
So now, this is even, even zeros, even ones. If you get a 0, then you have an even number of, this is an even number of zeros. The first E is for the zeros and the second is for the ones. So if you get a 1, now the number of ones is odd. If you get a 0, then the number of zeros is odd. And if you get a 1 here, if you get a 1, then you have odd. And here, if you get a 0, you have odd. Okay, now what remains? So what if you get a 0 here? You go back. You get a 0, you go back. If you get a 1 here, you go back. If you get a 0, again, go back, and 1, go back. Which one should be the accept state?
The bottom left.
Has an even number of ones, so even number of ones, odd number of zeros. So even ones, odd zeros. This is the state that we want. Okay, so this is the idea. So this is the AND. This is the AND in a DFA. So you track basically 2 properties, and the number of states that you need is going to be the product of the number of states that you need for each property. You're tracking 2 properties, right? So basically, this is the intersection. Again, you can generalize this for constructing a DFA for the intersection of 2 languages. So this is the intersection of the language with even ones and the language of odd zeros. And the intersection is going to be, to construct the intersection, you need the cross product of the 2 states, because you're tracking both properties. Okay, so this is the idea. So again, try to learn ideas and techniques. Don't memorize solutions to questions. Because in the test, I'm going to test your learning of ideas and techniques. I'm not going to ask you the same questions. So try to learn the ideas. Okay, we still have time. Okay, so this is another. By the way, I think the DFA questions are not straightforward. W such that W treated as a binary number is divisible by 4. Okay, so what makes a number divisible by 4? Yeah.
Just a question. Do we not have to define each state after doing the problem? Like Q0 is the state where we want to define all of them.
Okay, that's a good question. The question is not asking you to do this, so you don't have to, but it's a good idea always to define what each state means. In fact, it's always a good idea to write some comments, to write a line or 2 lines explaining the idea behind your DFA or NFA. So it's a good idea to say, okay, to describe this, I need a state for even odd to describe this. So using text to describe what you are doing is a good idea, but it's not required here. But try to make your solution clear. Okay, so divisible by 4. What makes a binary number divisible? What do the binary numbers that are divisible by 4? What do they look like? Yes.
I came up with they always have 2 zeros at the end.
Yeah, exactly. The numbers that are divisible by 4 end with 2 zeros. So we need to check for numbers that end with 2 zeros. So the 2 zeros is going to take us to an accept state. But we should also accept what? What's the number, the only binary number that doesn't end with 2 zeros but is divisible by 4? Yeah, 0. Yeah, so we should also account for this corner case. The 0 by itself, it does not end with 2 zeros, but it's a multiple of 0. So, okay. So we should accept the 0 by itself. But now, what if we get a 1? If we get a 1 in the first state, we should go to a certain state in which we are waiting for 2 zeros. So if I get a 1, I should go to a state where I'm waiting for 2 zeros. So this is where I have seen, I haven't seen any, or this state indicates that the last symbol seen was a 1, and I'm waiting to see 2 zeros. Now, so this is a 0 that takes me to an intermediate state, and then the second 0 is going to take me to this accept state. Now, we should figure out the rest of the transitions. Okay, now here, what are the transitions? What if I get a 1 here? Well, I go to this state. Whenever I get a 1, this is the state where the last thing seen is a 1. So this state here, the description of this state is, if I give them Q0, Q1, Q2, Q3, and Q4, Q2 means last symbol seen was a 1. So whenever the last symbol seen is a 1, you should go back to this. So, which means that if you get a 1 here, where should you go? Q2. If you get a 1, again go to Q2. Because it means that the last thing that you have seen is a 1, and you are waiting to see 2 zeros. Okay. Did we complete all the transitions? So 2 transitions. What will happen here if I get a 0?
You just
Interested.
suppose.
Yeah, you stay. because I have seen 2 zeros. And if I get a third zero, or a fourth zero, or a fifth zero, that's still okay. More zeros are good, but a 1 is going to take me back to this state. Okay, do I have all the transitions now?
Q needs to loop to itself.
Okay, Q2 needs a, what if there is a 1 here? Yeah, you stay. Does this complete all the transitions? I think so. I think now we have 2 transitions, 2 transitions, 2 transitions, 2, yeah. So in the DFA, make sure that you explicitly define all transitions. Okay, I'm going to do the last 2 very quick. So the last 2, we need the empty set, a DFA for phi. So you need a DFA that doesn't accept anything. And to construct a DFA that doesn't accept anything, don't put an accept statement there, right? So you don't want to accept anything. So just this state, and anything will just trap you in a non-accept state. And this is a DFA for accepting nothing. Now we need a DFA for accepting epsilon and only epsilon. Now we should accept something. We should accept epsilon. So how do we do this? Make it an accept state, but if you get anything, go to a trap state. Okay, so we went through question 1. So